this is a very important topic, and therefore the students will be able to understand each and everything about this chapter. To start with, I should say what is radiation, because simply we talk about the radiation and matter. Matter, of course, everybody knows about it, but let me first define what is radiation. It is the emission or the transmission of energy in the form of waves or particles through space at the speed of light. You know that whenever an electron is accelerated, it emits energy in the form of radiation. So first of all, we should understand what that electromagnetic radiation or electromagnetic spectrum. I am not going to give you the chart of that electromagnetic spectrum. I just mentioned what are the components of the electromagnetic spectrum. You know that gamma rays, X-rays, ultraviolet radiation, visible light, infrared radiation, microwaves, and radio waves. And in radio waves, we have got SW, that is short wave, MW, medium wave, LW, long wave, in the increasing order of wavelength or in the decreasing order of frequency. For example, the frequency of gamma rays is of the order of 10 raised to 22 hertz, and the wavelength corresponding to 0.001 nanometer. And coming to the last one, that is the radio waves, the frequency is of the order of 10 raised to 6, and the wavelength is of the order of 100 to 500 or even 600 meter. So now, according to the syllabus, we have got electron emission. You know that in metals, the outermost electrons are loosely bound to the nucleus of an atom, and such electrons can be detached from metal surfaces by different processes, and the process is called electron emission. Under the electron emission, first one, let us think of discharge of electricity through gases. This method makes use of electricity through gases at low pressure. The operators consist of, I have not shown the operators here. Of course, you are able to follow what that operators is. The operators consist of a glass tube with two electrodes fused into the tube at its ends. It contains a gas at low pressure of the order of 0.001 millimeter of mercury. A high voltage of the order of 10,000 volt is applied between the electrodes and start discharge of the molecules of the gas are ionized by collision, resulting in ions and electrons. Let us say, instead of using the word electrons, negatively charged particles, and positive ions bombard the cathode. Cathode rays, in other words, beam of electrons, are produced, and these cathode rays were discovered by William Crookes in the year 1870. And before 1897, it doesn't mean that the electron was not there earlier to 1897. It was there, but J.J. Thomson was the first scientist to determine experimentally E by M of the cathode rays. It was in the year 1897. You know J.J. Thomson model. According to J.J. Thomson, an atom is a solid mass of positive charge in which the negatively charged particles are embedded. And in an atom, there are equal number of positive and negative charge, and therefore atom is electrically neutral. And this concept of negatively charged particle was shown by J.J. Thomson in the year 1897, and that is how the electron came into picture. Thermo-ionic emission, and this is a process by which electrons are emitted from hot tungsten, and this was discovered by Thomas Alva Edison in the year 1883. When metals are heated, the free electrons get separated from the hot surface. And also you know about the Richardson-Dashman equation, and actually they derived an equation for thermionic current. J equals AT squared e to the power of minus 5 by kT, where J is the current density, that is actually the thermionic current density. A, capital A, which I have used, is the constant of proportionality. And T, capital T, is the absolute temperature. K is the Boltzmann constant, and phi the work function. And then another important process is photoelectric emission. Whenever the metals like sodium, potassium, rubidium, when they are exposed to ultraviolet radiation or visible light, the electrons are ejected from the metal surface. In the case of metals like alkaline metals like potassium, sodium, the electrons are emitted even under the influence of the visible light. Whereas in the case of zinc, etc., only the ultraviolet radiation is required, and when ultraviolet radiation is made to fall on zinc, cadmium, etc., the electrons are emitted. But in general, the electrons are emitted when the substances are subjected to high energy radiation such as gamma rays or X-rays. In fact, this photoelectric, the electrons which are emitted are called photoions or photoelectrons. This phenomenon was observed in the year 1887 by Henry Hertz. Then another emission process is cold emission. And in this process, strong electric field is applied to metal surfaces. Then free electrons are ejected even at room temperature, and hence it is called cold emission. It is also called the field emission because the electric field is applied and therefore the electrons are emitted. The other process is called the secondary emission. In this process, a beam of electrons with large kinetic energy is directed towards a metal surface, and these electrons which are ejected with large kinetic energy are called the primary electrons, and these primary electrons transfer some of their energy to the metal surface, leading to free electron emission. So like this, we have different types of electron emission, and I hope you have followed these types of electron emission. And before we go for the dual nature of light, we should understand the concept of light quanta. In order to understand this light quanta, it is necessary to understand the nature of light. Under the first one, we think of the corpuscular theory of light. Newton proposed this theory in the year 1672. According to Newton, the light particles are in other words called corpuscles, and these corpuscles are emitted from a luminous body. When once the corpuscles are emitted from a luminous body, they travel along straight line with enormous speed. And we can compare these corpuscles or the light particles to that of a bullet fired from the gun. You know, when the bullets are fired from the gun, they travel along a straight line before they fall into the ground. Like that, even here also, the corpuscles are emitted and they travel along a straight line, and thus even the rectilinear propagation of light was introduced based on this corpuscular theory of light. But one important thing which we have to notice here in the Newton's corpuscular theory of light is the speed of light is more in denser medium than that of the rarer medium, which is against the Foucault's experiment. The Foucault experiment was done in the year 1850, and that experiment showed that the velocity of light is more in rarer medium than that of the denser medium. No doubt the corpuscular theory of light was able to explain only the phenomenon of reflection, but it could not explain the phenomenon of refraction. In fact, to explain the phenomenon of refraction, the corpuscular theory suggested that the velocity of light is more in denser medium than that of the rarer medium, and this is the photo of Newton. Coming to the next one, I told you that the corpuscular theory of light could not explain even the refraction. In fact, it was failed to explain the simultaneous reflection and refraction. And in the year 1678, Huygens introduced the Huygens wave theory of light. According to Huygens, the particles are emitted. When they are emitted from a luminous body, they travel in the form of wave. So like what we see when the disturbance is created in a medium, the waves are produced exactly in the same way. Here, the particles, when once they are disturbed, the waves are produced, and these particles are traveling in the form of waves. He assumed that the longitudinal wave nature of light, and further he also assumed that for the propagation of the wave motion, a medium is required, and that medium is nothing but the ether medium, which fills the empty space as well as the material medium, and therefore it is called luminiferous ether or all-pervading medium. Of course, the Huygens wave theory of light suggested that the velocity of light is greater in rarer medium than that of the denser medium, which was in support of the Foucault experiment. The Huygens wave theory of light explained successfully the simultaneous reflection and refraction of light waves. Based on Huygens wave theory, in the year 1800, Thomas Young explained the phenomenon of interference, and Fresnel explained the phenomenon of diffraction. Of course, to explain the phenomenon of interference and diffraction, the longitudinal wave nature of light was sufficient. But polarization could not be explained based on the longitudinal wave nature of light. And therefore, Fresnel suggested that the light waves are transverse in nature. So with this assumption of the transverse wave nature of light, reflection, refraction, interference, diffraction, and even polarization were explained. But still, ether remained as an inconclusive medium at that stage. And now coming to electromagnetic theory of light. The electromagnetic theory of light was proposed by James Clerk Maxwell, and according to this, electric and magnetic fields oscillations produce electromagnetic wave. In fact, electromagnetic wave is produced in a direction mutually perpendicular to electric and magnetic field. And here I will just show you the Maxwell's equations. Of course, you have got the Maxwell's equation in your portions. Divergence E is equal to rho by epsilon naught. And rho is, the charge, and epsilon naught is the permittivity of free space. And divergence B is equal to 0, where B is the magnetic field, and E, what I have used earlier, is the electric field. Curl E is minus del B by del T, and curl B is mu naught J plus epsilon naught delta E by delta T. J is the current density, mu naught is the permeability of free space. We can even write it as divergence D is equal to rho. That means if we are using D, that is the dielectric displacement. There is a relation between the dielectric displacement and the electric field. That is D is equal to epsilon naught into E. And of course, he established, based on these four equations, the velocity of an electromagnetic wave is c is equal to 1 over square root of mu naught epsilon naught, where mu naught is the permeability of free space and epsilon naught is the permittivity of free space. Mu naught is 4 pi into 10 raised to minus 7 Henry per meter, whereas epsilon naught is 8.854 into 10 raised to minus 1. Okay. Then let us come to the electromagnetic, rather, before I come to the quantum theory of light, what was the success and what was the failure of the electromagnetic theory of light? The electromagnetic wave theory, in short, we call it as wave theory. It explains the phenomenon of reflection, refraction, interference, diffraction, all that. But it failed to explain, in fact, I should say that from what is that Rayleigh-Jeans and Wien's law. Wien's law, Rayleigh-Jeans law were based on the electromagnetic wave theory. Wien's law explained the black body spectrum at smaller, lower temperature and smaller wavelength, but it failed to explain at higher temperature and longer wavelength. On the other hand, the Rayleigh-Jeans law explained the black body spectrum at higher temperature and longer wavelength, but failed to explain the black body spectrum at lower temperature and smaller wavelength. There was no one formula to explain the black body spectrum at all temperatures and all wavelengths. It doesn't mean that the Wien's law or the Rayleigh-Jeans law failed in their theoretical aspect, because they assumed the electromagnetic theory of light, which is a continuous phenomenon, and that electromagnetic theory concept was not in favor of explaining the black body spectrum at all temperatures and all wavelengths. It is because of that, actually, Max Planck introduced the quantum theory to explain the black body spectrum. And he established a formula. That formula is nothing but E is equal to NH nu, where N is equal to 0, 1, 2, 3, etc. H is the Planck's constant that you know, 6.6025 10 raised to minus 34 joules second, and nu is the frequency. No doubt, the Max Planck's formula, that is E is equal to H nu over e to the 1 over 1 minus e to the power of h nu by kT, which explains the black body spectrum at all temperatures and all wavelength. In fact, the Planck's formula can be used to derive even Wien's formula, Wien's displacement law. Wien's displacement law, you can notice here. In fact, in this, you can see that with higher temperature, the peak getting shifted toward the shorter wavelength. And this was explained actually by Wien's displacement law. And Rayleigh-Jeans law, Stephan's law, all that were explained by Max Planck under the limiting condition. The major deviation from the electromagnetic theory to the Planck's quantum theory is that the energy is not in a continuous fashion, but with discrete packets, and these discrete packets are called quanta, and that formula is already given. Planck stated that quantum is either completely absorbed or completely emitted in optical process. A quantum. Later on, the word photon was coined by G.N. Lewis in the year 1926. George Newton Lewis, and he was the person to coin the word photon. And during that 1900, it was only called quantum. And this quantum, it cannot be broken or there is no fractional photon. For example, if we take a red bulb of 40 watt, emitting red photons. The wavelength of the red light here, I am taking approximately 700 nanometer. The energy of the red photon, you can write it as E is equal to h nu. That is equal to hc by lambda, because nu is equal to c by lambda. Suppose you substitute the values, it is like 6 point that Planck's constant, and velocity of light 3 into. And one more thing, like I forgot to mention, that the velocity of an electromagnetic wave as per the Maxwell theory is 3 into 10 raised to 8. And he suggested the light wave is also an electromagnetic wave. And therefore here I am substituting the values, and 700 nanometer, which we can write it as 10 raised to minus 9 here. And if you simplify that, it comes out to be 3 into 10 raised to minus 19 joule. The number of photons emitted by 40 watt bulb, and we can use the formula like this: nhc by lambda, or P is equal to Ne. Therefore, N is equal to P by E. That is 40 watt bulb we have used, let us say 40 watt over 3 into 10 raised to minus 19 on simplification of this energy, and it comes out to be 10 raised to 20 photons. We may be, there may be a question like, can we see the photons? The number of photons emitted per second is of the order of 10 raised to 20. And because of such a large number, naturally we will not be able to see from our eyes. The discrete nature of radiation cannot be seen, and that is why we will see only as a continuous light. Even then, the light beam cannot be seen in a free space. Only in a dust medium, the beam of light is visible, and you know that. The quantum theory of radiation brought in the corpuscular aspect of light into a combined picture. In fact, you can write the corpuscular nature with a straight line, and wave nature with a sinusoidal wave, and photon, it includes both the corpuscular and the wave nature. That means it is moving in the form of wave. And quantum theory of light, no doubt, explained the phenomenon of black body spectrum. Then photoelectric effect. Yeah, I will come to that. Einstein made use of the quantum theory of light to explain the photoelectric effect. But anyway, the photoelectric effect was explained by Einstein, making use of the Planck's quantum theory of radiation. But even atomic spectra was explained using quantum theory. But quantum theory could not explain the wave nature, such as interference, refraction, and polarization. And it is because of this, the wave particle duality, that is what our heading is, dual nature of light. This concept of dual nature of light was introduced in the year 1924 by de Broglie. So, like what I have already told you, that interference, diffraction, and polarization can be explained only on the wave nature of light. But the photoelectric effect can be explained only with the group of particles, and these group of particles, in other words, called photon, which is based on the quantum theory. Thus, light has dual nature. That means it has both the wave nature as well as the particle nature. That is why the definition is given in the beginning. Radiation is a process, either you may call it as emission or transmission of energy in the form of waves or particles. So this is what about the quantum theory. then electromagnetic theory, and thus the wave particle duality. That means, according to de Broglie, not only the duality in nature is not only confined to light, but it is the characteristic of material particles such as electrons, protons, neutrons. Based on relativity and quantum mechanics, he means de Broglie established an equation, and that equation is lambda is equal to h by p, where lambda is the wavelength, which exhibits the wave nature, and p is the momentum. That momentum is nothing but m into v. That is the particle nature. And h is the Planck's constant, which I have already mentioned that. And this equation, lambda is equal to h by p, is called the de Broglie wave equation. In fact, in other words, it is also called the matter wave equation. So now, coming to this photoelectric effect, and the photoelectric effect was actually discovered by Heinrich Hertz in the year 1887. And before that, in the year 1864, Maxwell published his theory of electromagnetic radiation or electromagnetic wave, which I have already explained. And thus, Hertz proved the existence of the electromagnetic radiation experimentally. What is this experiment? You can see here, this is the schematic diagram, and you can see here, this is the experiment conducted by Hertz in the year 1887, and this experiment establishes that electromagnetic wave. Or you can see here, this is an induction coil, and in an induction coil, you know the number of turns in the primary is less and the number of turns in the secondary is more. The number of turns in the secondary is of the order of thousands, and the number of turns in the primary is about few turns. And you can see here, the upper one is the plate A, square plate, and the lower one is another plate B. And these two plates A and B act as a capacitor. You know, for a capacitor, there must be two parallel plates, and these two are the parallel plates. And these two plates are connected to metallic spheres S1 and S2, and they are connected by means of a thick wire, or in other words, you may call them as metal rod. And these two are connected to the secondary of the transformer, rather the induction coil. The primary of the induction coil is connected to a battery, a DC power supply, which is of the order of about 10 volt or even less than that. You know that when breaking the circuit, when the high voltage of the order of 10,000 volt is produced in the secondary coil, and when such a high voltage is produced, and these plates, actually A and B, acquire high potential difference, and when once the potential difference between the plates is sufficiently large, the air gap which you have got there gets ionized and starts conducting. Consequently, the capacitor discharges quickly, and there is small inductance of the plates, and connecting rods discharge in the form of damped oscillatory current of very high frequency, which we call it as electromagnetic wave. Due to the discharge of the capacitor, the potential difference between the plates falls and the air gap stops conducting. However, the capacitor is discharged again to a high potential during break. Like this process of charging and discharging of the capacitor generates trains of electromagnetic waves with electric vector parallel to the gap and magnetic vector at right angles to it. I told you in the beginning that the electromagnetic wave is produced in a direction mutually perpendicular to electric and magnetic wave vectors, or displacement vectors. And in order to detect these radiations, Hertz employed a circular metallic ring, which you can see at the front with a gap at one point. This circular ring is placed near the knobs, that S1 and metal spheres I said, S1 and S2, in such a way that the magnetic lines of force cut it. This results in induced EMF in the ring, and hence the sparks occur in the gap of the circular ring between A and B. This detector has a natural frequency of its own depending on the values of L and C, and by suitably adjusting the size of the ring and also the distance between A and B, frequency of the ring can be made equal to the frequency of the electromagnetic radiation. And Hertz was able to measure the electromagnetic radiation of wavelength 6 meter and frequency about 50 megahertz, that is 50 into 10 raised to 6 hertz. And Hertz discovery is that a metallic surface is capable of emitting electrons when light of very short wavelength falls on it. The photoelectric effect was discovered in the year 1887, and again in the year 1888 Hall was established with the help of the gold leaf electroscope. You can see here, this is the gold leaf electroscope. When UV radiation fall on this zinc plate connected to the gold leaves, the gold leaves collapse, and he explained that phenomena is due to the emission of charged particles from the metallic zinc plate when exposed to radiation. The gist of that experiment is like this. When ultraviolet light is incident on a neutral zinc plate, the plate becomes positively charged because the electrons are emitted from it. When ultraviolet light is incident on a negatively charged plate, it loses its charge rapidly. When UV light is UV means ultraviolet light is incident on positively charged zinc plate, it becomes more positively charged. He came to the conclusion that only negatively charged particles can be then the surface under the action of UV light. And I have already mentioned that in the year 1897, J.J. Thomson discovered the electron, and even before this electron was discovered, all those things were discovered. And now let us come to the experimental study of the photoelectric effect. In the year 1902, Philip Leonard conducted the experiment on photoelectric effect. And this is the photo of Philip Leonard, and I am not going to explain who that Leonard is, but this is the experimental setup. And in this experimental setup, normally the commutator is provided, but in the diagram which I am showing you, the commutator is not shown. Here on the left side, photocathode, which is a thick plate, and this photocathode may be made up of any alkali metal. And if we can use visible light, if we use visible light, even the alkali metal is enough for the emission of photoelectrons. But in case if we go for zinc, cadmium, etc., we have to go for ultraviolet light only. And on the right side, we have the anode, which you may call it as a plate. And you can see here, the cathode is connected to negative. Yeah, cathode or anode depending on how we connect the supply. If the negative of the battery is connected to the plate, then we call it as a cathode. And here, of course, this is the cathode. And positive is connected to the anode, in other words, which is nothing but the plate. Of course, I have shown here as ammeter, but the current obtained here is not of the order of ampere. It is only of the order of microampere. At the best condition, it is of the order of milliampere, but not in the form of ampere. Anyway, this is an ammeter. It is in the range of micro range. What happens when light is incident on the photocathode? The electrons are emitted, and you know the anode is given the positive potential. When the electrons are emitted, they are emitted, but at the same time the anode is given the positive potential. Therefore, whatever the electrons are emitted from the cathode, they are attracted by the anode. Suppose we increase the potential. We increase the potential means that is why this arrow mark shows that it is variable potential difference. If we keep on increasing the potential difference, then the number of electrons emitted from the cathode will be more, and the electrons which are emitted from the cathode will be attracted by the anode, and thus we have the current. And the experiment is normally done by varying the intensity of radiation, frequency of radiation, potential difference between the plates, and then the nature of the material of the cathode. What is that intensity of radiation? The intensity of radiation, I mean, we can go for different wattages. Maybe let us say 40 watt bulb, 60 watt bulb, 100 watt bulb, like that. We can either use different wattage of light source or light bulb, or even if we say that we want to use only a single source, maybe of 40 watt, then we have to vary the distance. You know about the inverse square law, that I proportional to 1 over d square. That means as the distance increases, the intensity decreases. Therefore, the intensity variation can be done with the help of either varying the distance or by changing the light source with a different wattage. And frequency of radiation, I mean, light of different frequencies can be used by putting appropriate color filters, in other words, colored glass, in the path of light falling on the emitter, which is nothing but the cathode. And next, of course, potential difference. I told you that the potential difference can be increased, and even it can be decreased, and we can also change the polarity of the battery. That means cathode can be connected to the negative of the battery, cathode can be connected to positive, and the anode can be connected to negative of the battery. In fact, we can increase the voltage in the positive sense, decrease the voltage. And here, several scientists have done that experiment. Leonard, Richardson, and Compton, R.A. Millikan. In fact, R.A. Millikan did the photoelectric effect experiment later in the year 1916. I will again come back to that. And studied the different aspects of photoelectric effect. The results of their finding can be summarized in the form of laws called the photoelectric effect. In fact, normally the photoelectric emission is an instantaneous process without any time lag. And that is of the order of 10 raised to minus 9 seconds or even less. Usually in the textbook, this will be given at the end. But anyway, to highlight that the photoelectric emission is an instantaneous process, I have given that in the beginning itself. So in the textbooks, normally it will be given at the end, but here I am giving you in the first place itself. The photoelectric emission is an instantaneous process. And we should know about the threshold frequency. For a given emitter, there is a definite minimum frequency nu naught called the threshold frequency, below which there is no photoelectric emission, and photoelectric effect takes place only when the radiation frequency of radiation is greater than the threshold frequency. The threshold frequency is different for different emitter. It doesn't mean that the frequency is same for all cathodes or for all emitters. It is depending on the material. And suppose we multiply the threshold frequency with the Planck's constant, the product is h nu naught, and that product h nu naught is called the work function. In other words, it is also called the threshold energy. The work function for alkali metals is less, is of the order of 2 eV, but for zinc and other things it is about 4 eV. And that is why the alkali metals cause photoelectric effect even with visible light. For incident frequency greater than the threshold, that's what I have already mentioned, that the kinetic energy of the photoelectrons varies directly as the frequency of the incident radiation, but it is independent of intensity. You can see in this graph, this is nu naught, which is the threshold frequency, and this is the energy. In other words, it is the kinetic energy. That is the energy with which the photoelectrons are emitted. As the frequency increases, the kinetic energy increases linearly. That is what you can see. Then coming to effect of intensity of light on photocurrent. Keeping the frequency of the incident radiation and the accelerating potential, that is nothing but the potential difference fixed, the intensity of light is varied. Photoelectric current increases linearly with intensity of light, provided the frequency is greater than the threshold frequency. Or we can put it, the photoelectric current is directly proportional to the number of photoelectrons emitted per second. We can even put it as the strength of the photoelectric current is directly proportional to the magnitude of the photoelectric current. That means if the intensity increases, the magnitude of the photoelectric current increases, but not the kinetic energy. The kinetic energy increases only with the frequency. And now coming to effect of potential on photocurrent. So we keep the frequency of the incident radiation and the intensity fixed. The positive potential of anode is gradually varied, and the photoelectric current increases with increasing in potential. All the, with increase in potential, all the emitted electrons are collected by the anode plate, and photoelectric current becomes maximum or saturated. Further increase in accelerating potential, photocurrent does not increase. This maximum value remains the same. In other words, it reaches the saturation current. On the other hand, if negative potential is given to the anode and positive to the cathode, that is reversing the potential. With the help of the commutator, one can easily change, rather reverse the voltage. But here in my diagram, I have not used the commutator. Please try to look at the diagram where the commutator is given. So when we give the negative potential to the anode and positive to the cathode, the electrons are repelled, and only most energetic electrons are able to reach the anode plate. Again, not all the electrons will be able to reach, only few, but at a certain critical value of the negative potential, which we can call it as V0, the photoelectric current becomes zero. This value is called cutoff or stopping potential. This stopping potential repels even the most energetic photoelectrons. And with the maximum kinetic energy, we can put it as K maximum is equal to EV naught, where E is the electronic charge, V naught is the stopping potential. If the experiment is repeated with incident radiation of different intensity, in the sense higher intensity, I2 greater than I1, the saturation current found to be higher value, it is found that the stopping potential is independent of the incident radiation. And this is what you see in the picture, this diagram. The stopping potential is same even though we vary the intensity. That means the stopping potential remains the same, and if we increase the intensity, the photoelectric current is more for source of higher intensity compared to the lower one. And here you see that I2 greater than I1. So photoelectric current is along y-axis, and then the voltage is along x-axis, and this stopping potential is constant. Let us come to another effect, frequency of incident radiation on stopping potential. You can see here, as frequency is varied, the stopping potential varies in the sense as frequency nu3, nu2, nu1. Nu3 greater than nu2, nu2 greater than nu1, but the stopping potential or stopping voltage V3 greater than V2 greater than V1, but the saturation current remains the same. So that is what here I have used. The stopping potential are in the order V03, V02, V01. If the frequencies are in the order V3, V2, V1, this implies that greater the frequency of the incident light, greater is the maximum kinetic energy of the photoelectrons. Consequently, greater retarding potential. We worked on different values of stopping potential. Of course, I have already, on the basis of, yes, coming to this. On the basis of the electromagnetic wave theory, the time required for an atom, for the time required for the electron to be emitted from an atom uh, uh, is of the order of few minutes, even if the intensity of beam is very high. But if the intensity of the beam is very low, it may go for few minutes or days for a faint beam. And experiment shows that the electron emission is instantaneous. That's why I told you in the beginning that the experimental observations of Leonard and others showed that the photoelectric effect is an instantaneous process, and the time lag is only of the order of 10 raised to minus 9 seconds, whereas the electromagnetic wave theory also explained the photoelectric effect, but for the emission of electrons from a metal surface, it requires few seconds if the beam is very high, and if the beam is faint, it may take few minutes or even days. And that is the difference between the explanation given by the electromagnetic wave theory and the experimental fact about the photoelectric effect. And according to electromagnetic theory, light of larger intensity emit larger kinetic energy, but actually it is found that the imparted kinetic energy of photoelectron is independent of the intensity. It only depends on the frequency. Also, velocity of the photoelectron should be independent of the frequency of incident light, but experiments show that greater the frequency of incident light, greater will be the velocity of photoelectrons emitted. The previous speaker, Professor Shivananda Kanavi, was mentioning about the Einstein. In fact, in the year 1905, Einstein explained the photoelectric effect based on Planck's quantum theory of light. I told you that the Planck's quantum theory of light was introduced in the year 1900. In fact, Max Planck was terribly, that's what in the literature says, that Max Planck was literally upset, thinking that no one was able to use the Planck's quantum theory. In fact, it was Einstein who used that quantum theory, Planck's quantum theory, and explained the photoelectric effect. And according to quantum theory, light consists of quanta or corpuscles of energy h nu, which move through space with the velocity of light. Like what I have already explained about the threshold energy or the work function, phi naught is equal to h nu naught. And if the frequency of the incident radiation, according to Einstein, if the frequency of the incident radiation is less than the threshold frequency, no photoelectric effect takes place. And if the frequency of the incident radiation is equal to the threshold frequency, photoelectric effect just takes place. On the other hand, if the frequency of the incident radiation is greater than the threshold frequency, then photoelectric effect takes place. In addition, the kinetic energy is imparted to the electrons. And the Einstein photoelectric equation is half mv square is equal to h nu minus h nu naught. Or even we can write it as half mv square is equal to h nu minus phi naught, because phi naught is the work function. This equation was established by Einstein. That's what I told you already. And this photoelectric equation, this half mv square, even we can write it as EV naught. That is what I will show it here, and then I will come to Millikan's experiment. EV naught is equal to half mv square. I have given that h nu is equal to h nu naught plus half mv square. And h nu, we can also even write it as h nu naught plus EV naught. Either you can write it in terms of phi naught or h nu naught. And this we can modify as h nu minus h nu naught over E is equal to V naught. That is the stopping potential. And H is equal to EV naught over nu minus nu naught. And suppose we plot a graph, and you know that we get the slope, and slope is nothing but the Planck's constant, and that Planck's constant is found to be 6.625 10 raised to minus 34 joules second. In fact, that's what I mentioned that in the beginning, that Millikan, that was in the year 1916, he thought that he can disprove the Einstein's photoelectric equation. He conducted, rather he repeated the photoelectric experiment with all the details like what others have done it, thinking that he was able to disprove the Einstein's photoelectric equation. But even though he did the experiment, that's what again I have repeated here, positive potential, then negative potential, all that what was done previously for the photoelectric experiment, everything was repeated by Millikan later, that was in the year 1916. But he found that whatever the equation given by Einstein was correct, and thus that was in the year 1921. Einstein got the Nobel Prize. Of course, in this year, rather last year, 2021, we celebrated the Einstein's photoelectric, Nobel Prize on photoelectric effect. Centenary year of the Einstein's photoelectric effect, and even Millikan accepted, and that is how this equation we have.